Hello, good day everyone. I'm 𝗟𝗃𝗱 from the Department of Electrical and Electronic Engineering of University Tunku Abdul Rahman, Malaysia. Now, I would like to present my paper with the title Deep Learning and Optical Character Recognition for Digitization of Meter Reading. This is the outline of my presentation. First is the introduction. Industrial Revolution is the transition of agricultural and handicraft economy to industrial and machine manufacturing economy. Currently, we are in the fourth revolution, and the ultimate goal of IR 4.0 is to attain smart factory with fully automated processes. The major element in IR 4.0 is digitization. According to the research by 𝗟𝗃𝗱𝗏, IR 4.0 has the following advantages, mainly on increasing productivity and reducing production cost. Although many meters nowadays come with the smart IoT features, which provides real-time monitoring and data storing, many industries still prefer to continue using the existing analog meters in their manufacturing plants. One of the reasons analog meters are still preferred is the relatively high cost of the smart meters. Besides, various types of smart meters from different suppliers are required for different manufacturing processes. Divergence in the electronic communication protocols used by each meter becomes a challenge to integrate them into the single monitoring and control platform, which requires extra expenses. The aim of this paper is to propose a cost-effective image recognition system to capture and digitize the analog meters readings using a deep learning model and an optical character recognition, OCR. The objectives are as listed. This is the overview of the system operation. It consists of 6 major operations. Firstly, the self-trained deep learning model is loaded into the system. Next, the image of the meter can either be captured directly using a camera or loaded from the storage. The deep learning model is used to perform inference on the image to localize the meter reading area. Subsequently, the region of interest containing the readings is extracted. Thereafter, the ROI undergoes image processing for noise removal and quality enhancement. Lastly, the optical character recognition is used to recognize the digits. Next is the methodology and results. The deep learning model used in the proposed system is based on the SST MobileNet V2. This model is chosen because it requires lesser processing power and storage than other conventional models, such as VGG, ResNet, Inception, and AlexNet. It is suitable to be deployed in resource-limited devices, such as low-cost mobile phone or embedded system, which is Raspberry Pi. The model is trained in TensorFlow via Google Colab with a GPU accelerator. A dataset containing 750 meters images has been prepared and labeled with the label image software. The types of meter images in the dataset include analog water meter, gas meter, and electricity meter. These images have been collected via self-capturing and online platform, such as Google Image. Figure 2 shows the examples of meters images in the dataset. A portion of the images, that is 250, has been generated with augmented technique to increase the variability. The techniques applied include flipping, rotation, brightness changing, and hue changing as illustrated in Figure 3. The dataset is divided into an 8:2 ratio, which 600 images are used for training and 150 images for validation. Figure 4 shows the examples of inferenced images by the deep learning model. It can be observed that the meter readings area has been framed with detection box. Next is the region of interest extraction. It's important to extract the ROI by removing the area outside the detection box and keeping the area within the box, where the meter's reading is located, so any unintended characters will not be recognized during the OCR process. The ROI extraction can be achieved using the contour detection function in OpenCivic. The meter's image that has been inferenced by the deep learning model is first converted to HSV format using the color space conversion. Since the detection box is green, the lower and upper limits of the HSV values are defined as shown in the slide. Next, the image is compared with the defined limits using the inch range function to obtain a mask containing only the detection box outline and its position. After that, the fine contour function is used to locate the box outline, and a new mask with the ROI in white is created using draw contours. Next, the bitwise AND operation is performed on the meter image with the mask. Subsequently, the ROI vertices are obtained using the NumPy min and max functions. These vertices values are essential for the cropping out of ROI. Lastly, we can observe that the ROI has successfully been cropped out. Next is the image processing. It is to remove the noise and enhance the quality of the extracted ROI. This step is crucial to improve the accuracy of the OCR. According to the official documentation, the Tesseract OCR engine prefers the characters in black and white, and the characters should be resized to at least 300 dpi of resolution. The ROI is first enlarged to 3 times of its original size using the resize function in OpenCivic. The superior interpolation method of intercubic is used to enlarge the image. It performs bicubic interpolation over a 4 × 4 pixel neighborhood and outputs a clear enlarged image as desired. Subsequently, the enlarged ROI is converted to grayscale using the CVT color function. It is then thresholded to binarize the grayscale image into black and white only by converting the value of each pixel to either 0 or max, depending on the threshold defined. It can be observed that most of the noises have been removed. Next is the optical character recognition. The ROI extracted in previous step is in matrix form. However, the Tesseract can only operate with the image in PIL format. First, the first step is to convert the image format. Next, the segmentation mode of PSM7 is used as the characters are in horizontal orientation. The res.sub function is used to eliminate unnecessary spacing and symbols being recognized. Figure 6 shows the output of the OCR as in string data type, indicating that the success of digitization. Here is another sample of meter image being recognized and digitized. Next is the system evaluation. The size of the deep learning model with trainings of 15,000 is about 10 megabytes, which is appropriate for resource-limited applications. Figure 8 shows the graphs of various loss functions for the training process of the deep learning model. It can be observed that the curve of the total loss function is approaching constant as the training steps increases. First, the training process is stopped to avoid overfitting. The accuracy evaluation of the system is based on 2 aspects, namely the accuracy of meters readings region detection by the deep learning model, as shown in equation 1, and accuracy of character recognition in equation 2. The accuracies are being averaged with the total images evaluated. Table 1 shows the results of accuracy evaluation, which both aspects achieve more than 90%. The table also shows the comparisons to related work. From the evaluation process, it's noticed that the accuracy of the meter's readings region detection by the deep learning model is affected by the size and resolution of the meter images. When the meter faces are small, which is occupying less than 30% of the whole image, there is higher chance that the deep learning model detects the false area. First, it's recommended to place the camera near and center to the meter face. Figure 9 shows the example of fault detection, which the image brightness is low and the meter face is distant from camera. Besides, the OCR engine is sensitive to skewing of the character. Hence, it suggested that during the capturing process of the image, the camera should be placed steadily with respect to the meter's face orientation to optimize the performance. In conclusion, this paper presented the digitization process for the meter's readings using deep learning model and optical character recognition. The deep learning model and program developed have achieved accuracy with more than 90%. The solution provided can be used as an alternative for achieving automatic remote monitoring of meters reading without a huge investment in expensive digital meters. Lastly, the authors would like to express their deepest gratitude to University Tunku Abdul Rahman, Utah, and the Center for Railway Infrastructure Engineering, CRIE, for their supports. Thank you, and hope you have a nice day.